So let's look at some homework problems out of 8.5. So one problem says that we have two forces, a 32 Newton force and the 52 Newton force acting at right angles or at 90 degrees to each other. They want us to find the magnitude and the direction the resultant makes with a smaller force. So since they don't tell us specifically which direction either force is going, we can't really say which direction the resultant is, but we can describe its direction in relation to one of the other vectors. So when they say that we have these two vectors at a right angle, imagine that we have a point, and from that point, we have a 30 Newton force going in one direction, a 52 Newton force going some direction that is perpendicular to that. So it could be going up or down. But the idea here is that the angle between them is 90 degrees. Now, when it says it's 90 degrees, that means in relation to this point that they're both acting on. Another way to draw this same diagram is to say here's the object we're pushing on. One object is pushing this direction, one is pushing this direction, or it could be pushing down. Either way, that means they're perpendicular to each other. Notice, it's not going to let me slide it, but if we took this one and slid it up, and took that other one, slid it over, this vector and that vector are equivalent because imagine they're the same length and they're in the same direction. Likewise with this one and that one, and those are perpendicular. So let's call this one the 32 Newton force and this one the 52 Newton force. So that's the direction the vectors are going, but that's not how we add them together. Anytime we add vectors together, we have to add them tail to head, meaning from the tail of one vector, we put the head of the other vector, or from the head of one, we put the tail of the other. So let's take this 52 Newton force, let's slide it to the head of this one and draw it in the same direction as the 52 Newton, just now we're tail to head. So the resultant would be from where the 32 Newton vector starts to where the second vector ends. You can think of it as a path. If we do this path and then that path, the resultant is from where we started to where we stopped. But these are forces instead of paths. So if that was 90 degrees, then that's 90 degrees, which is going to make that also 90 degrees. Well, since that's 90 degrees, we don't have to use law of sine or law of cosine to get our resultant. We can use Pythagorean theorem to get the magnitude of our resultant. So r squared is 32 squared plus 52 squared. So 32 squared plus 52 squared. That makes 3728. And if we take the square root of both sides, then we get r is 61.1. And that's in newtons. So that's the magnitude of the force. Now to get the direction that the resultant makes with the smaller force, this is the smaller force, this is the resultant. So we're looking for that angle. We know the side opposite of that angle, the side adjacent. So tangent theta is 52 over 32. So if we do 52 over 32 and take inverse tangent, we get an angle of 58.4 degrees. So that's the angle here. Now this one was a little bit more simple than some because our triangle is a right triangle. But in some of the examples, that's not going to be the case, and we can't simply use the Pythagorean theorem, or we can't simply just use tangent. So let's look at another example. So let's do this one. This one says we have a 400 427 Newton force and the 610 Newton force, and they are acting at 46 degrees between each other. The angle between those two forces is 46 degrees. So if we draw one of the forces, doesn't matter which one, the other one, this would be the same direction, so a 46-degree angle would be something like this. So we could call this one 427 and this one 610. So that's the orientation that the vectors are. So imagine that we had a point here and someone was pulling this direction, someone was pulling that direction. There's a 46-degree angle between their forces. But to get the resulting force is going to be somewhere in between here. So remember, we have to put our vectors tail to head. So let's take this slanted one and let's slide it down. So the easiest way I can do that is I can just make a copy of it and slide it down. So this vector and this vector are equivalent, as I just made a copy. Now my vectors are tail to head. So our resultant is here. Now we have this side and that side, but we don't have an angle inside the triangle. And this resultant does not bisect 46 degrees. But what we do know is that if we were to continue that line out, this angle and this angle are corresponding angles. So that angle is 46 degrees. From here to here, that's a straight angle, 180 degrees. So 180 minus 46, that leaves us with 134 degrees for this other side. So if we want to get the magnitude of the resultant, we can use law of cosine because we have an angle between two sides. So r squared equals 427 squared plus 610 squared minus twice their product times cosine of the angle between them. So now we just have to do this arithmetic and we can find out what r is. So 427 squared, 182, 329, plus 610 squared, 372, 100, and then when we do the next term, we have negative 2 times 427 times 610 times cosine of 134, and that's 361, 875. And notice that's positive. I put a negative in with my calculation. Negative times positive times positive times negative. Well, two negatives make a positive. So that comes out to be positive. So if we take that and add 372, 100 plus 182, 329, 182, 329, if I could type it in, we get that, so that's r squared. So r is just the square root of that. So whatever that is, take the square root. So about 957. These forces are in newtons, so this force will also be in newtons. Notice that's less than what we would get if we just do that force plus that force. Because in order just to add those, they would have to be pointing in the same direction. If one car was pulling this direction with this force, another car was pulling in the same direction with that force, then the resulting force would be their sum. But since they're not in the same direction, you can't just simply add the numbers together. We have to use the triangle. So then we also want to find the angle that the resultant makes with the smaller force. So here's the smaller force, here's the resultant. So we need that angle. We have an angle side pair, So we can use law of sines to get theta. So sine theta over 610 equals sine 134 over 957. So if we multiply both sides by 610, we get sine theta equals 610 times sine 134 over 957. So that's what sine theta equals to. And then if we take inverse sine, of that, we get 27.3 degrees. And that is the value we want. We don't want the answer to that equation that's in the second quadrant, because that angle is obviously not obtuse. We already have an obtuse angle, so we can't have another one. So the angle that the resultant makes with the smaller force is 27.3. Let's do another one. Another way that they give us some problems is they say that the magnitude of one vector is a certain value. The magnitude of another vector is another value. And the angle between those two vectors, and they give you that angle. So then they want us to find the resultant and the angle that the resultant makes with, I think they're probably going to ask us the angle the resultant makes with u. So if we draw u, doesn't matter which direction, because it doesn't specify the direction of u. It just says that the angle between u and v is 20. So if u is in this direction and v makes a 20-degree angle with it, we can draw it this way, where this is 20 degrees. So those are not aligned tail to head. So if we slide this one down, now they are tail to head, where this is 39, this is 21. If this is 20 degrees, that's 20 degrees. That would make this angle 160 degrees, because this angle plus that one have to make 180. So our resultant is here. So if we want to find the magnitude of the resultant, 39 squared plus 21 squared minus twice their product times cosine of the angle between them, and that'll give us r. So real quickly, 39 squared plus 21 squared minus, and I'm going to put this in parentheses, I'm doing 2 times this times this times that. So minus 2 times 39 times 21 times cosine 160. So when I close the parentheses, that gives us the result of that. So 3501 is what that should come out to be. So if we take the square root of both sides, we get r is about 59.2. Or we could call that 59. So that's the length of the resultant, the magnitude of it. Now if we want the angle that so let's not call that theta, because theta is this whole angle here, so let's just call that alpha. So if they want to know alpha, sine alpha over its opposite side equals sine 160 over 59. So multiply both sides by 21. So sine alpha is sine 160 times 21 divided by 59. So we get that decimal for sine. If we take inverse sine, then we can get alpha. So about 7 degrees. So that's this angle. And that's the magnitude of the resultant. So let's do one more. Let's do a word problem where they tell us that an airplane with an airspeed, and they give us the airspeed, 150 kilometers per hour. The direction of its track is 70 degrees. Or they said, or that could be considered its course. There's a wind. The speed of the wind is 29 kilometers per hour. And it's coming from a direction of 340 degrees. So when it says that the wind is coming from 340 degrees, we have to be careful there. So if we put north here, then 340 degrees is roughly that direction, but that's where the wind's coming from. So the wind is coming from that direction with a magnitude of 29 kilometers per hour. "70 degrees is the direction that the airplane is going. So not actually its heading, not where it's pointed, but that's where it's going. So 70 degrees would be somewhere like so. So essentially that's the resultant. When we add the heading that the airplane is pointed, the person in the pilot seat points the airplane in a certain direction, the wind blows it off course, and this is the result of where it goes. So if we have this force and another force that get added together to make that, imagine that we slide this force down to here. Then the heading, or where we have to point the airplane, would be somewhere like this. So this is 29 here. If we dot this line out here, then if that's 70, then that's 70. If this is 340, then that's 20, which would make this part here also 20. If that's 20 and that's 70, then that's 90, which would make that also 90. One part that makes this problem tricky is what they mean by airspeed. Airspeed is the velocity that the airplane would be going if there was nothing pushing against it. So 150 is not the plane's resulting speed, but that's basically the speed that the engines propel it in still air. So this is the direction the airplane is pointed. This is its airspeed. We have this angle. We have the 29. Let's see if we can move it. Not very easily. 29 is this magnitude. So we have two magnitudes. We have an angle. So that's three pieces of a triangle. So we should be able to solve for the rest. So what we're looking for is the direction that the airplane needs to be pointed, which is essentially that angle. That's his heading if we need to end up going this direction. But that angle is not going to be one we can find directly necessarily, or wouldn't be the ideal one. So let's find this angle. Since this is a right triangle, we can say that from this side That's the opposite side. That's the hypotenuse. So sine of alpha is 29 over 150. So if we take inverse sine of 29 over 150, we get about 11 degrees. So if this part is 11 degrees, and from here to here is a 70, then what we want to know is this angle. Let's call that beta. So if we take the full angle 70, subtract the part that we're not looking for, that we've already used, that'll tell us what's left for beta. So beta is 70 minus 11, or about 59 degrees. So the trick here is just knowing what the terminology is there.